Okay, so we're in section 2.5 now. We're talking about a really important property of many functions that we call continuity. And I think the best way to introduce this is to do a comparison between two graphs. So if you look over here, we have the graph of this function f, and then the graph of this other function, which doesn't have a name. And if we compare the two, you might find a number of similarities and differences, but the one that I want to focus in on is what would happen if you had to draw each of these graphs by hand. So notice if I were to sketch the graph of f shown here, at least the part that I can see, if I were to sketch that out with my pen, I could do that entire curve without having to lift my pen up. I could just do it in one continuous motion. This graph down here appears to have a break in it right here where x is equal to -1. So if I wanted to sketch the part of the curve that I can see here, I would have to do this part, lift my pen up, and then finish it with this parabolic looking curve here. In this case, we would say that this function has a property called continuity. And this function does not possess that property. It possesses what we call a discontinuity when x is equal to -1. That's that break that I'm talking about there. So that's kind of an intuitive explanation of what continuity is. But as we've already seen, the intuitive definition for a mathematical concept can only get us so far. So we want to give a more mathematical definition. And don't worry, this definition will not be like the kind that we saw in 2.4. We're not dealing with epsilons and deltas here, although we could reframe the definition of continuity using an epsilon delta type of definition. We're not going to need to do that. So here's how we define a continuous function. Or to be a little bit more specific, a function that is continuous at a specific number. We say that a function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Now there's actually, your book will say that there's three things that are implied by this, and I'm just going to talk about them. First of all, this is implying that the expression on each side of this equation is defined in the first place. If the limit as x approaches a of f of x was not defined, then it could not be equal to anything. Same here, f of a. So we're assuming that a is in the domain of our function f because it's being plugged in right here. We're also assuming that the limit as x approaches a of f of x exists. Remember, oftentimes limits fail to exist for one reason or another. And then third, aside from those two assumptions, that these two things are equal to each other. This graph right here is sort of expressing why this definition of continuity conforms to our idea of sketching a graph without having to pick up your pen, okay? So this graph, this function f is continuous at the number a. And the reason for that is if you look at the curve here, as x approaches a from either direction, we are approaching this point right here. But this point happens to also lie on the curve, and that would give us f of a if we plugged a in to our function. So the limit is approaching the actual point that already exists on the curve, which is basically what this definition is saying. If that's the case, then I should be able to sketch this part of the curve going through that point without having to pick my pen up, okay? Now, when a function fails to be continuous at a specific number, there are different ways in which that can happen. And we're going to use the same term that we said before. If a function is not continuous at some value x equals a, then we would say that f is discontinuous at a. Or another word that we'll use probably more often is we'll say f has a discontinuity at a. So before we look at different kinds of discontinuities, I want to mention something about continuous functions. There is another way of characterizing continuous functions which kind of shows why they are useful and show up as often as they do in real-world applications. When a function is continuous at a specific number, then what that implies is that a small change in our independent variable near that number it's continuous at will produce a relatively small change in our dependent variable. So small changes in your inputs will correspond to relatively small changes in your output. Okay, so to illustrate that, again, let's take a look at maybe this continuous function right here on this little graph. If this is a, then plugging a into my function gives me this value f of a. Okay, now if I make a very small change in my input, let's call that a plus h. Find the corresponding output, and it's not much further than f of a. So this small change here produced a small change here. This would be f of a plus h. Okay? Compare that to this function that's discontinuous. So if I choose a to be right here, right, and then maybe a plus h is over here, a small change in a, if I compare these outputs, that's f of a right there. I want this guy right here. Compared to this is f of a plus h. This small change corresponded to a very large change in my dependent variable. Okay? In fact, if you want to go so far as to think of this function as a position function, where your dependent variable is giving you the position of some moving particle, for example, and maybe your x-axis represents time, then this jump from this value all the way down to this value is the equivalent of that moving particle just teleporting, instantaneously moving a large distance with essentially no time passing from here to here. So we don't really see teleportation much in real world applications, which is why discontinuities of this nature don't appear as frequently as a continuous function would in the kinds of applications we see in the real world. But there are discontinuous functions that do show up, and we might see some of those. So let's take a look at an example here. We have a graph of some function, and our goal here is to identify the discontinuities in this graph. Okay, I'm going to talk through them. I'm not going to write down all of the reasoning for why each thing that we identify is a discontinuity, but we're going to talk through them. So let's start here. Going from left to right, I see that there's a hole in the graph. Okay, and I don't see any point to find anywhere else. So what that indicates is that if we're calling this function f of negative 2 doesn't exist. There's no point anywhere corresponding to an x value of negative 2. So right away, this function cannot be continuous at negative 2 because the right-hand side of this thing, if a was equal to negative 2, just doesn't exist in the first place. The limit as x approaches negative 2 does exist. It's equal to whatever this value would be. But that's irrelevant for continuity because we need both of those things. So we have a discontinuity where x is equal to negative 2. Where else do we have a discontinuity? Well, at negative 1, we have a discontinuity because we have what appears to be a vertical asymptote. And remember, functions are not defined at those asymptotes. There is no value that we can get by plugging negative 1 into whatever this function is because there's no point that lines up with that negative 1. So negative 1 gives us another discontinuity. Notice these two values gave us discontinuities, but graphically they look very different. One of them looks like a little hole where the graph sort of connects on both ends to that hole. The other one looks like an asymptote. So already we're seeing that discontinuities can take different forms. At x equals 0, we have yet another discontinuity. Okay, so I'm going to put 0 down. Now, what is the issue here? Well, f of 0 does exist because there's a point here. So whatever number this is on the y-axis, f of 0 is equal to that number. But the limit as x approaches 0 does not exist because in my limit, as I approach from the left, we're going towards this positive value, but as I approach 0 from the right, we're approaching this negative value. So my left and right-hand limits do not agree with each other, which means the limit doesn't exist there. That means that the left-hand side of this defining equation here for continuity doesn't exist, and so we don't have continuity there. Notice I have a similar issue appearing right here. f of 1 is defined. It's a point right here. But once again, this right-hand limit and this left-hand limit do not go to the same value. So the limit as x approaches 1 of this function f of x does not exist. I have discontinuities at all of those places. Okay? So let's take another look at discontinuities. This time we're going to focus on something that we don't have a graph of. Okay? We want to identify where this function is discontinuous. Okay? So this is a piecewise function, and there are a couple of places where piecewise functions can experience discontinuities. First of all, let's pretend for a moment that this was not a piecewise function. Let's just look at f of x equals 2x plus 1. You know that the graph of that function is a line. And lines, if you go with the most basic idea of what continuity looks like, you can draw a line without picking up your pen. So lines are graphs of a continuous function. Linear functions are continuous. That's another way of saying that. Continuous at every real number. But this piecewise function only allows us to use this linear expression when x is less than or equal to 1. This function right here is a rational function, and we know that rational functions are defined anywhere where their denominator would not be equal to 0. So I can see that this guy is not defined when x is equal to 2. And I also notice that it's appearing where my domain restriction here says that I use this expression anytime x is greater than 1. Well, 2 is greater than 1. So 2 is going to cause us a problem here. I already know that we're going to have a discontinuity at x equals 2, simply because this function is not defined there. You can't find f of 2. It doesn't exist. So is that the only discontinuity? Well, maybe, maybe not. There's one other issue that you can run into with piecewise functions. And I'm going to return to this example over here. This looks like the graph of a piecewise function. It looks like our piecewise function would be defined as a linear function for all values of x less than or equal to -1, and as a quadratic function for all values of x greater than -1. Both of those functions just by themselves are continuous everywhere, but because the piecewise function causes this split at -1, it may create a discontinuity simply because the two graphs don't connect. So how do we verify that when we don't have a graph to look at? Well, we see that the split would happen at x equals -1. So I want to see if, using my definition of continuity, I want to see if the limit as x approaches 1 of f of x is equal to f of 1. Let's look at that limit. We've done limits of piecewise functions before, and we've seen that you need to look at their left and right hand limits first. So let's take the limit as x approaches 1 from the negative side of f of x. That would be the same thing as the limit as x approaches 1 from the negative side of 2x plus 1, because when x approaches 1 from the left, we're using values of x that are less than 1 to approach. That means we're looking at this part of our piecewise function. Because that function is linear, we can use direct substitution. We've seen that in the limit laws section. 2 times 1 plus 1 would be 3. The limit as x approaches 1 from the positive side of f of x, we need to look at that next, would equal the limit as x approaches 1 from the positive side of 1 over x minus 2. When x is approaching 1 from the positive side, we're using values of x that are greater than 1, indicating that we're looking at this part of our piecewise function. This function, I can use my limit laws because I'm not getting a denominator of 0 if I plug a 1 in. I can use my limit laws to bring the limit up into my numerator and denominator and evaluate them directly. I get the same thing that I would get using direct substitution. 1 minus 2 is -1. 1 over -1 is -1. Notice how these are not equal. Okay? Because they're not equal, the limit as x approaches 1 of f of x does not exist. Okay? Remember, if that limit doesn't exist, then we can't even talk about continuity there. We would say that it's not continuous or discontinuous. So we have discontinuities when x is equal to 2 or 1. There are no other places where we would find a discontinuity, so that's all of them. Okay? Let's look at another function. This time it's not piecewise, but we want to identify a discontinuity in the function f of x equals x squared plus x minus 12. And we're asked this additional question: what small change can be made to this function to remove this discontinuity? Might be a little confusing what that means, but we'll try to make sense of it. So notice, first of all, it's a rational function, and as we've kind of seen now, rational functions are going to be continuous everywhere except for where they're not defined, and this rational function is not defined at 3. So I'm expecting a discontinuity at 3, x equals 3, okay? That's the only place I'm expecting to see a discontinuity, but I want to look a little more closely at this function. So f of x is equal to x squared plus x minus 12. I can factor that. That's equal to x minus 3 times x plus 4 over x minus 3. And notice we get cancellation, x plus 4. But remember, it's not just x plus 4. It's x plus 4 provided that x is not equal to 3. And remember, that's because in the original function, 3 was not in the domain. So if we simplify this, we get an equation for a line. We get an expression that's linear, and linear functions are defined everywhere. So we have to add the exception to this, that x is not equal to 3. Now what does this function look like? Well, if this is 4 right here, we're looking at a line with a slope of 1 and a y-intercept of 4. Now let's suppose 3 is right here. This function is going to have a hole right there. Okay? And again, that's to indicate that this function looks like a line everywhere except for where x is equal to 3. The function just won't be defined at 3. So that is actually what this original rational function would look like if you graphed it. And you can check that in a graphing calculator. Graphing calculators usually fail to put this open circle here. So you have to know that that's there. Now it says, what small change can be made to this function to remove this discontinuity? We know there's a discontinuity there because a hole indicates a discontinuity. The function's not defined there. But what would it mean to remove that discontinuity? Well, it would mean to turn it into a continuous part of our function by plugging it up with another point. I want to put a point in there, okay? But how do we do that? Well, if this function did not have this restriction, if x was allowed to equal 3, then I could plug 3 into this. 3 plus 4 would give me 7. So I want this thing, I want to add the point 3, 7 to my graph here, because then that would plug that hole, and now I have a continuous line. But how do we redefine f of x to make that happen? Well, let's call this new function g of x, and let's set it equal to this. X plus 4, I'm going to change that. G of x. Let's set g of x equal to my original rational expression, x squared plus x minus 12 over x minus 3, specifically when x is not equal to 3. And then I'm going to set, when x is equal to 3, I'm going to set g of x equal to 7. Okay? So because the limit of this function existed even when the hole was there, I could create continuity by putting a point where the limit would be taking me. And that's what this piecewise function down here is doing. For that reason, discontinuities of this type, where the limit exists but the function is not defined there, or if the function is defined but just happens to not equal the limit, that would mean that we have a point somewhere else at when x is equal to 3. We can remove that discontinuity by adding another little point in there. Okay? And for that reason, we call those types of discontinuities removable discontinuities. Down here, I identify 3 types of common discontinuities that we see. So The first kind we just talked about. A removable discontinuity at a is the type of discontinuity where the limit as x approaches a of f of x happens to exist. That's what was happening here before we plugged the hole. There was a limit that existed. They both approached the same value, 7 in this case, but the limit does not equal f of a. Whether because f of a doesn't exist at all, like in our example up there, or if f of a is just a different value. We call that a removable discontinuity. Jump discontinuities are these types, where the graph, as you approach a, whatever a happens to be, is approaching one value as you go from the left and a different value as you approach from the right. It creates a jump. Up here I described that jump as teleporting, right? So a jump discontinuity is one where the left and right hand limits of f as x approaches a both exist, but they don't equal each other. They equal different values. Notice that would imply that the limit doesn't exist, but the left and right hand limits do. They just go to different places. An infinite discontinuity is what you get when f has a vertical asymptote at x equals a. That's what we saw here. Okay? Those are not the only 3 types of discontinuities that exist. There are others, but these are the 3 most common types. Okay? So here is a few more graphs kind of illustrating these points. This is a removable discontinuity. If you can see, there's a little hole in this graph. The limit as x approaches 2 appears to exist, but it's not defined at 2. The function is not defined at 2, so we have a discontinuity there. This is also a removable discontinuity. Notice this graph looks almost identical to this one, but in this case, f of 2 does exist. It's just equal to something other than what our limit would be as x approaches 2. So same thing, it's still a removable discontinuity. Here we have an infinite discontinuity, and that's because the limit as x approaches 0 from either direction, the left or the right, goes to infinity. We have a vertical asymptote there. Notice the function actually is defined at 0 because we included this point down here, but it's still a discontinuity. And then finally, this is the greatest integer function. This is, your book talks about this, we haven't talked about it, but it's a good example of jump discontinuities. You can see that the graph jumps from little bar to bar here. And again, if you took 1 as an example, as x approaches 1 from the left, my function is approaching 0. If you approach 1 from the right, the function is approaching 1. So my left and right hand limits disagree with each other. Okay? We'll save these definitions for the next video.